My name is Kah Jian. I'm from Faculty of Chemical and Energy Engineering, specifically in Pure Chemical Engineering program. This is the video for System Deconstruction Analysis Report for KitKat software. This is the overview of this video. It consists of 3 parts, and each part contains 2 tasks. Part A is foundational knowledge and system overview. Task 1 is software engineering fundamentals, and Task 2 is system domain and requirements concepts. Part B is system analysis and deconstruction, and Task 3 is requirements engineering, Task 4 architecture and testing analysis. For Part C, software modeling and design, the Task 5 is use case diagram, and Task 6 is activity diagrams. Let's move on to Part A, Task 1, Software Engineering Fundamentals. The software development life cycle, or known as SDLC, consists of 7 phases that guide the development of a software project. The first requirement is gathering and analysis, where the development team identifies and understands the user's need. Next is planning, where the project scope, timeline, budget, and resources are determined. Then comes to system design, where the software architecture, user interface, and database are planned. After that is implementation, where the developer writes source code based on the design. Once the software is built, it enters the testing phase to identify and fix bugs and ensure it meets the requirement. The software is then deployed so that the user can start using it. Finally, the maintenance phase provides ongoing bug fixes, updates, and new features to keep the software reliable and meet the changing user needs. Skipping any phase of the SDLC can greatly increase the risk of a software project failing, because every phase has an important purpose. For example, if the requirements phase is skipped, developers may misunderstand what the users actually need and build the wrong features. Skipping the design phase can result in a poorly structured system, while skipping testing may leave bugs and security issues undiscovered. Ignoring maintenance also makes it difficult to fix problems and improve the software after release. As a result, the project may exceed the budget, miss deadlines, and fail to meet the user requirements. By following every phase of the SDLC, developers can produce software that is reliable, high quality, and successfully solve the intended problem. This is Part A, Task 2, System Domain and Requirement Concepts. The software that I selected is KitKat software. KitKat software is an open source software used for designing electronic circuits and printed circuit boards, or PCB. It provides several key functions that support the entire PCB design process. Firstly, users can draw circuit schematics by creating electronics diagrams using components like resistors, capacitors, and microcontrollers. After that, they can design PCB layouts by arranging components and routing copper traces on the board. KitKat can also help to ensure the design quality by allowing users to run design rule checks and electrical rule checks to detect errors before manufacturing. This is important because it reduces the mistake that could cause the circuit failure. Finally, once the design is complete, KitKat can generate manufacturing files such as Gerber's file, due files, or a bill of materials. These files are used by the manufacturers to produce and assemble the physical circuit boards. Overall, KitKat supports the full workflow from circuit design to manufacturing preparation. Now I'm going to talk about differences between functional requirement and non-functional requirement. Functional requirements refer to the specific tasks or features that a software system must provide in order to meet the user needs. It describes what the system actually does, such as logging in, processing data, or generating outputs. On the other hand, Non-functional requirements describes how well these features should perform, that focuses on the quality and performance of the system rather than its specific functions. A simple way to understand the difference is by using real-life example of a car. The ability to start the engine, accelerate, and brake are all functional requirements because they define what the car can do. However, aspects such as fuel efficiency, safety, comfort, and how smoothly the car runs are non-functional requirements because they describe how well the car performs those functions. Both types of requirements are equally important. Without functional requirements, the system would have no purpose, and without non-functional requirements, the system may work but perform poorly, be unreliable, or provide a bad user experience. Together, they ensure a complete, usable, and high-quality product. In KitKat, there are two important non-functional requirements, which are performance and reliability. Firstly, the performance requirement ensures that the graphical canvas can smoothly render multi-layer PCB designs without any cursor lag or shuttering. This is very important because PCB routing requires high precision, and even a small delays when placing or adjusting the traces can interrupt the workflow and potentially lead to design errors. Secondly, the reliability requirement ensures that the system automatically saves the project in the background every 5 minutes. It also guarantees that the most recent saved state can be fully recovered after a system crash or power failure. This is critical for KitKat because PCB design is time-consuming and often takes several hours. Without proper auto recovery, user could lose a large amount of work, which will cause delays in prototyping and manufacturing. Overall, these two non-functional requirements are critical to ensure KitKat is stable, efficient, and suitable for professional PCB design work. In KitKat uses a document wheel architecture, which is a simplified version of the model wheel controller pattern. In this architecture, the system is separated into two main parts, the document and the wheel. The document is responsible for storing all the important PCB design data in the background, such as component positions, netlists, and design rules. It represents the actual content of the project, independent of how it is displayed. The wheel, on the other hand, is what the user sees on the screen, such as the schematic editor and the PCB layout canvas. It focuses only on displaying the data in a visual and interactive way. When user performs an action such as moving a component on the board, the change is first applied to the document. After that, the wheel automatically refreshes to reflect the updated state. This ensures that the data and the display stay consistent at all times. This separation between data and interface makes KitKat easier to maintain, improve system organization, and allows users and developers to update or extend the features without affecting the core design data. KitKat uses This figure shows the use case diagram for KitKat. The primary actor is the hardware designer, who interacts with the software to design and prepare a printed circuit board, or PCB, for manufacturing. The designer performs several main tasks, including creating the circuit schematic, updating the PCB from the schematic, routing the PCB board, running a design rule check, and exporting the manufacturing files. There are two important relationships shown in this diagram. The first one is the include relationship between route PCB board and update PCB from schematic. This is a mandatory step because the PCB must first receive the component placement and electrical connections from the schematic before routing can begin. The second important relationship is the extend relationship with the Run Design Rule Check, or DRC. This is optional because the designer can choose to run the DRC at any time during the routing process to detect the issues such as unconnected pins or trace clearance violations. These relationships help to ensure that the PCB is designed correctly and is ready for manufacturing. This figure shows the activity diagram for the generating manufacturing files use case in KiCad. It illustrates the step-by-step process a hardware designer follows to export a PCB design for manufacturing. The process begins when the user opens the plot menu and configures the output settings, such as selecting the file format and save location. Next, the system checks whether the selected output folder is valid. This is represented by the decision node in the diagram. If the folder is invalid, the system displays an error message and asks the users to choose another location before continuing. If the folder is valid, KiCad first generates the Gerber files, which contain the PCB layer information, and then creates the NC-DUE files, which specify the dewing locations for the board. Finally, the user closes the dialog, and the manufacturing files are ready to be sent to the PCB manufacturer. This workflow helps ensure that the export process is completed correctly and without any errors. This figure shows the activity